Welcome to Spelling Bee Ninja, where we believe that education should be engaging and accessible for everyone. If you are eager to delve into mathematics with us, you're in the right place. Subscribe now for free educational content that inspires learning and fosters a passion for knowledge. Together, let's explore the fascinating world of functions and the mathematical relationships that shape our understanding of the world. Today, we're diving deep into the concept of functions in mathematics. At its core, a function represents a special relationship between two sets of numbers, known as ordered pairs. Imagine a machine. You input a value, and the machine processes it according to a specific rule, producing a single output. For example, if we have a function defined as f x equals 2x plus 3, by inputting the number 5, the output will be 13, derived from doubling 5 and adding 3. This foundational idea of functions is critical in algebra and serves as a tool for modeling relationships across various fields, including science, engineering, economics, and even our everyday lives. Fun fact alert! The idea of a function was formalized in the 18th century by the brilliant mathematician Leonhard Euler, who also introduced the notation f, x. Isn't it fascinating how such a simple concept has evolved over time and remains a cornerstone of mathematics? Moving on, let's discuss domains and ranges, two essential concepts that help us fully grasp the nature of functions. The domain refers to the set of all possible input values, or x values, that a function can accept. Conversely, the range represents the set of all possible output values, or y values, that a function can produce. For instance, for the function f, x equals x squared, all real numbers can be used as input, which defines our domain, while the output is limited to non-negative real numbers, forming our range. This limitation is why understanding domain and range is crucial. In real applications, domains can sometimes be restricted based on practical scenarios. For example, negative time doesn't make sense in most contexts. Now let's shift gears to the difference between functions and relations. You might wonder, aren't they the same? Well, not quite. A relation is any set of ordered pairs that describes a connection between two sets of elements. A function is a specific type of relation. In a function, each input corresponds to exactly one output. It's like having a well-organized library. Every book, input, has a defined place on the shelf, output. A helpful tool to determine if a graph represents a function is the vertical line test. If any vertical line intersects with a graph more than once, the relationship fails to be a function because that would imply a single input has multiple outputs. This visual method is remarkably effective in quickly assessing whether a graph represents a function. Next up is function notation, which makes working with functions easier and clearer. Rather than using the traditional y equals 2x plus 3, we express it as f, x equals 2x plus 3. In this format, f is simply the name of the function, and x represents the input value. To evaluate the function, you replace x with your desired value, say, 5. So, f, 5, equals 2 times 5 plus 3, yielding an output of 13. Function notation simplifies working with multiple functions at once. You can have f, x, g, x, h, x, and more, making it easy to keep track of which function you're discussing. Now, let's explore the different types of functions because the world of mathematics is rich with diversity. We encounter linear functions, which graph as straight lines due to a constant rate of change and are expressed by the formula f, x equals mx plus b. A quadratic functions graph as parabolas and are represented as f, x equals x squared plus bx plus c. Exponential functions, in contrast, illustrate rapid changes or decay, as seen in f, x equals a times b raised to the power of x. Polynomial functions encompass sums of terms with variables raised to whole number powers. Finally, trigonometric functions, such as sine and cosine, describe periodic phenomena. Each function type models different real-world situations, revealing the seamless connections between mathematics and our environment. Speaking of connections, let's discuss the slope of a linear function. The slope measures a line's steepness and direction, calculated as the rise over the run in m equals the change in y divided by the change in x. In the linear function f, x equals mx plus b, m is the slope while b is the y-intercept. A positive slope indicates an upward trend, a negative slope signifies a downward trend, a zero slope means the line is horizontal, and an undefined slope means it is vertical. The concept of slope isn't just theoretical, it has real-world applications. from calculating the steepness of a hill to determining the pitch of a roof. Next is the y-intercept, the point where the graph crosses the y-axis. In the linear function f, x equals mx plus b, the y-intercept is given by b. To find it, simply set x to 0 and solve for y. This value often represents a starting condition, such as the initial cost in an economic model or the starting population of a species in biology. It's intriguing how much context can be crammed into a single point on a graph. Now, let's consider how functions manifest in real-life scenarios. They're everywhere. In science, functions are used to describe physical laws like how speed relates to distance and time. In economics, they help model supply and demand curves. Engineers employ functions in system designs and force analyses, while medical professionals utilize them to track drug concentrations in the body. Even in finance, functions are crucial for calculating interest rates and investment growth. A fun fact to highlight here: the Global Positioning System, or GPS, uses functions to determine your exact location based on signals from satellites. Lastly, let's unpack why functions are considered the backbone of algebra. Functions embody the fundamental relationships between quantities, serving as a systematic way to model various phenomena in our world. They elegantly link algebra, geometry, and calculus, allowing us to explore everything from simple linear relationships to complex systems. Understanding functions is crucial for anyone interested in pursuing a career in the fields of science, technology, engineering, or mathematics, often referred to as STEM. Serendipitously, the concept of a function is so central to mathematics that it's frequently called the heart of algebra, forming the basis of high school algebra courses. To recap our exploration today, we learned that functions represent unique relationships between input and output values. We discussed the importance of understanding domain and range, the differences between relations and functions, and helpful concepts like the vertical line test and function notation. Furthermore, we explored various function types, such as linear and quadratic functions, and their practical implications, including concepts like slope and y-intercept. Most importantly, we highlighted how functions pervade our lives, forming a crucial part of disciplines ranging from science to economics. Through our deep dive, we've understood why functions are the foundation of algebra, opening doors to advanced mathematical concepts. Thank you for joining us on this engaging journey into the realm of functions. We hope this lesson has illuminated your understanding and sparked your curiosity about how mathematics interweaves with the world around us. Don't forget to subscribe to Spelling Bee Ninja for more free educational content that makes learning enjoyable and informative. Until next time, keep exploring the wonders of mathematics and stay curious.